Hello. In this lecture, we are going to see about the compensators. What is the need for compensator? What are the types of a compensator, particularly lag, lead and lag lead compensator, its characteristics. In the next video, we will be working out few design problems using these compensators. Welcome to the lecture. If you look at this block diagram, this is a closed loop control system. If this closed loop control system, if this GC of S is your compensator, right? Okay, we are going to add this compensator externally to improve some performance measures. It can be like relative stability or speed of response, like that. Okay, if I'm going to add this compensator, that is GC of S, in cascade with the forward path transfer function G of S, then such compensation is called cascade compensation. Suppose if I am adding GC of S in feedback path with the forward path transfer function G2 of S, it is called feedback compensation. The compensation is why we do compensation is to achieve the objective, like to improve the relative stability. To achieve the speed of response, we go for compensation, and to reduce the steady state error also, we do the compensation technique. What are the type of compensators are? Is the lead, lag lead compensator. As I discussed, there are earlier the two types of performance measures can be given. One is the transient response, another is the steady state response. Okay, if you look at the second order underdamped system unit step response, it will be oscillating as well as exponentially decaying, right? So where it is oscillating is temporary, it is very little time. That response is called transient response. Permanently it is going to settle at 1. Such response is called steady state response. So complete response is nothing but transient response plus steady state response. Sometimes we need to improve the transient response, sometimes we want to improve the steady state response. So the conditions may be like transient response measures may be given, or can be like steady state response may be given. Okay, transient is what? This transient is called temporary or short lived. Okay, for some little time only this is going to exist. Okay, now this transient response either can be given in time domain specifications or frequency domain specifications. In time domain specifications, to improve the relative stability, the question may be given in the form of damping ratio or peak overshoot. Similarly, to improve the speed of the response, that is quickly the system outputs to settle, it can be given in the form of rise time, settling time, and undamped natural frequency of oscillation, right? This is your omega n. This oscillating frequency is your undamped natural frequency of oscillation, that is your omega n. Okay, so these specifications are given in time domain. Suppose I can give the specifications in frequency domain also, like resonant peak phase margin to improve the relative stability, resonant frequency bandwidth, that is your omega b, to improve the speed of the response. Okay, so what about relative stability? Relative stability in the sense, see, observe this expression, e power minus t by 2, e power minus t by 5, right? We know e power minus 5 is 0, e power minus 5 is very close to 0. So for what value of t this will become 0? When t is equal to 10, this will become 0. For what value of t this will become 0? For t equal to 25. So this will settle quickly, this will settle bit later. This needs t equal to 10 for settlement, this is t equal to 25 for settlement. These sort of things is called relative stability. Okay, now we have seen about the transient response measures. Okay, that too in time domain specifications and the frequency domain specifications. Next, after seeing transient response, we have to move into the steady state. How I mentioned the steady state? Steady state response is measured in the form of steady state error, right? You know, steady state error is your ESS. This is your steady state error. Steady state error is mentioned by the constant Kp, Kv and Ka. Positional error constant, velocity error constant, acceleration error constant, right? Okay, when I will use positional error constant, when I give a step input, I will use positional error constant. When I use ramp input, I will use velocity error constant. When I give parabolic input, I will use acceleration error constant. How can I find for step input? It is steady state error is equal to 1 for unit step input, steady state error is 1 by 1 plus kp. For unit ramp input, the steady state error is 1 by kv. For unit parabolic input, the steady state error is 1 by ka. Okay, if there are, so to improve the, for designing a system, they will be mentioning kv is of minimum some value design. These sort of specifications is given by the, to improve the steady state response, the specifications will be given in terms of kp, kv and ka. While designing a problem, we can understand these things very much easier, right? Now we look at into the basics of a compensator. First thing, we start with the lead compensator. A compensator is the one will have a 0 and pole, right? So I am mentioning the 0 as 1 by tau and the pole as 1 by alpha tau, where alpha is the ZC by PC. This ZC by PC is your alpha. I will take the condition that alpha is always less than 1. If the alpha is less than 1, then the compensator is called lead compensator. Okay. Now you can observe from this. Now we observe this pole 0 plot, right? Now I have marked the ZC here. Then the pole is minus PC, 0 is minus ZC. Okay. Now the 0 is very close to the imaginary axis, compared with the pole. Okay. Such compensators are called lead compensator. For example, if I take GC of S as S plus 3 and S plus 5, what is the 0? 0 is minus 3. What is the pole? Equate the denominator equal to 0. This is the pole. Okay. So this is the, so this is what compensator? This is a lead compensator. If the 0 is closer to the imaginary axis, I say it is a lead compensator when compared with the poles. Poles will come this side, to the left side of the 0. Okay, right. Now see, this is the standard form. I am writing ZC as 1 by tau, PC as 1 by alpha tau. Okay, I am going to take 1 by tau outside from the numerator, 1 by alpha tau from the denominator. Now the expression becomes like this, right? So 1 by tau will get cancelled. So 1 by alpha in the denominator comes to the numerator, it becomes alpha. So this is another form of expressing the lead compensator, right? So this form, this are all same. It's a different way of representing. That is the point you have to remember, right? All are the same lead compensator. Only condition is the 0 should be close to the imaginary axis. I have given an example, right? Okay, fine. And one more thing, this alpha, that is your ZC by PC, should be always less than 1. That you should keep in mind. Okay. Now again I have mentioned the, what is GC of S, right? Okay, I am going to write in frequency domain. In frequency domain, I replace S with j omega. This S is j omega. This S is j omega. So this is the frequency domain response or sinusoidal transfer function. Okay, fine. Now you observe what is going to happen at omega equal to 0. Omega equal to 0 means frequency is 0. Frequency is 0 means what is the meaning? The signal is a constant signal or a DC signal. When I put omega equal to 0, what happens to the transfer function? This term becomes 0, this term becomes 0. So GC of j omega is equal to alpha. Don't take it as infinite, right? It's alpha. Okay, alpha. So this alpha is the gain. But you know, alpha is less than 1. Okay, gain should be greater than 1. And I am saying that this alpha is less than 1. If the alpha is less than 1, I can say the gain as attenuation. Okay, think it's a common sense that gain means it should be greater than 1. Here the gain we get is alpha, which is less than 1. So I can say it as an attenuation. Okay, so this is an lead compensator circuit. Okay, and see, for lead compensator circuit, what I am doing is I have to cancel out this alpha. So I introduce an amplifier whose gain is 1 by alpha. So what happens when this signal is coming here? When this signal is coming here, this alpha and this 1 by alpha will get cancelled out. So we will have V naught as this expression. I have removed the alpha. Okay, I have removed the alpha, right? Because of an amplifier whose gain is 1 by alpha. So this is the standard form of a lead compensator. Okay. Now I am going to derive the transfer function of the lead compensator, right? So this is the input is here, output is here. I need the output voltage, right? To need the output voltage, what I do? I have to go for the voltage divider rule. So V0 is equal to total voltage, and what is its corresponding resistance? I am finding out V0 across R2. So corresponding resistance R2 divided by total resistance R2 plus this total resistance. What is the meaning? R1 and capacitor are parallel. In capacitor I can write in impedance form 1 by SC. So R1 parallel with 1 by SC. So I have to multiply and add those values. I get this value. So this is equal to this value. Okay. So coming back, so VI into corresponding resistance divided by total resistance R2 plus this value. On solving, these are simple mathematical manipulations, right? You can pause the video and can observe what I am doing. Okay, and taking best cross multiplying, taking this to the numerator, then I am writing in this format, right? Okay, this is what I get. Let us go into the, okay, yes, the same thing I am repeating here. Observe closely, this is a standard form. No, S plus 1 by tau plus S plus 1 by alpha tau. So what is tau? Tau is R1C. What is alpha? Alpha is, this comes to the denominator, right? Alpha is R2 by R1 plus R2, R2 by R1 plus R2, and R1C is your tau, right? I have written in the standard form. So this compensator, and we have found that this alpha is less than 1. So definitely this is a lead compensator. The circuit is a lead compensator circuit. How I concluded? Based on the alpha. R2 by R1 plus R2 is definitely less than 1, okay, because denominator is larger than the numerator. Now we will be finding out the response, right? Magnitude response and phase response. Okay, so this is the general transfer function. I have removed the alpha. In frequency domain I have written, in place of S I have substituted j omega. Now what is the magnitude? Magnitude is square root of real part square plus imaginary part square. I have done for the numerator and the denominator. Then what about the phase angle? Phase angle is tan inverse of omega tau by 1. For the denominator I put the minus sign, tan inverse of alpha omega tau. Okay. Now you observe very closely. If in a Bode plot, I have explained in a separate video how to plot a Bode plot. You can look at that video for additional information. But here I briefly explain what we are going to do. In a Bode plot we know whenever numerator is working, okay, whenever a numerator is working, numerator is working, it will contribute a plus 20 dB per decade. Whenever the denominator is functioning, it will contribute to a minus 20 dB per decade. Okay, this all happens after the corner frequency. What is the corner frequency? ZC is the corner frequency, PC is the corner frequency. What is ZC? 1 by tau. What is PC? 1 by alpha tau. Which is smaller value? Since this is very close to the imaginary axis, ZC is smaller when compared with PC. So numerator will work first, then denominator will work. Okay. So numerator will work after ZC. So after, that is your first corner frequency, it will going to, because of the numerator, plus 20 dB per decade. Okay. Then after the second corner frequency omega C2, denominator will function, so it will contribute to minus 20 dB per decade. So plus 20 dB, then minus 20 dB, net result is 0 dB, no change at all for the change in frequency. Okay. So this is the Bode magnitude of the Bode plot for this function. Okay. Now come to the phase part. For the phase part we know tan inverse ranges from 0 degree to 90 degree. Similarly this tan inverse is 0 degree to 90 degree. Okay. So if you look at the terms inside the bracket, this is omega tau, this is alpha omega tau. So this alpha is less than 1. That means this will work much better than this. Okay. So initially it will be positive. Initially, see, look at the, for the highest omega equal to 0, both are 0. So for omega low frequencies, angle is 0. At high frequency, very high frequency, the maximum angle is 90 for tan inverse. So the maximum angle for this is 90. So 90 minus 90 for high frequency it is 0. In between, it goes through the positive angle. Okay, it goes through the positive angle. Why it goes to the positive angle? Because this term works much better than this term. The reason is inside the bracket I have a smaller term when compared with this term. That is the reason. Okay, so we have a positive angle. Okay, right. Now we are going to find what is the maximum phase angle possible and at what frequency the maximum phase angle occurs. Okay, further what I am going to do is I know what is phi. This is the phase angle of the given lead compensator transfer function, and I am going to take tan on both sides, right? I am going to take tan on both sides. So what happens is, we know what is tan A plus B. Tan A plus tan B, 1 minus tan A tan B. Tan A minus B is this expression. Easy to remember is, see, if it is plus sign here, make it plus, the opposite sign comes the denominator. Tan A minus B, the numerator we have minus and denominator is in opposite sign. Okay, now I am going to take this term as A. This is my A, this is my B. Okay, this is my A, this is my B. So what happens? Tan A minus B. Okay, so tan A minus B, so tan phi is equal to tan A minus B. What is tan A minus B? Tan of, what is A? Tan inverse of omega tau. So tan inverse get cancelled, so we have only omega tau. What is then tan B minus tan B? What is tan B? Tan inverse of alpha omega tau. Tan inverse gets cancelled, we have this term. Okay, other things you can understand, right? This also you can do it very easily. Just I am putting in this formula. Remember, this is A, this is B. So tan A means this term, tan B means tan of this term. Okay, so this is my tan phi. Now we are going to find the what is the what frequency maximum phase lead occurs. That is your omega m. Okay, what is the maximum phase lead? If you look at this plot, at omega m maximum phase angle is happening. We are going to find what is omega m. Okay, to find the maximum value, what we do? We will just differentiate the phase angle phi with respect to omega, right? And I equate it to 0. This is, I take the numerator as u, denominator as v, uv relation I am going to use, right? So what is uv relation? Just I keep the numerator, I keep the denominator as it is, right? I keep the denominator as it is, differentiate the numerator, minus I keep the numerator as it is, differentiate the denominator, divided by the denominator square, right? Divided by the denominator square goes to the right side, it vanishes, so I didn't write that term. Okay, then equate, take the things to the right side, this expression to the right side. Then on solving, you pause the video and you can note down these things quite easily, right? Okay, I just used differentiation of u by v. This relation I have used, right? Okay, or I can say d by d omega. U is the numerator, v is the denominator. Okay, so you can observe these things. Pause the video, take the notes. So omega square I got. This omega, what is omega now? Square root of 1 by square root of alpha tau, right? So this is the max, this is the omega at which the maximum phase angle occurs. So this is my omega m. Okay, and there is another way of finding omega m, that is by taking geometric mean of the two corner frequency. What are the corner frequencies? You know what is the corner frequency? Corner frequencies are the ZC and PC. So this is the one corner frequency, 1 by tau. PC is the another corner frequency, 1 by alpha tau. Just you multiply and take square root, that we say as geometric mean. Okay, square root of, I am multiplying this omega c1 omega c2 and I am taking square root. That way also I can get the omega m. So you remember what is omega m is the frequency at which maximum phase angle occurs. That is your 1 by alpha tau. Okay, now I have to find what is the maximum phase, right? I know what is tan phi, right? If I need phi m maximum phase, in place of omega I have to put omega m. Okay, that is what I have done here. In place of omega I substitute omega m. What is omega m? 1 by square root of alpha tau. So this is the maximum. This tan phi m is the this is the maximum angle I can get. Okay. So I can represent this in sine form. How means, see, I construct a right angle triangle, and this is my angle phi. I am getting tan theta is equal to, we know it is opposite by adjacent. So opposite side is opposite to phi is your 1 minus alpha, adjacent side is 2 root alpha. Then I have to find what is x, that is your hypotenuse, right? How to find the hypotenuse? By using Pythagoras theorem, square root of opposite side square plus adjacent side square, right? So square root of 1 minus alpha square plus 2 root alpha square is 4 alpha. Okay, on solving we will be getting 1 plus alpha. So this is 1 plus alpha. So what is sine phi m? Sine phi m is opposite side by hypotenuse. Opposite side by opposite is 1 minus alpha, hypotenuse is 1 plus alpha. This is another way. Okay, if I need phi m, what I should do? Phi m means just you take sine inverse of 1 minus alpha by 1 plus alpha. Thereby you can find phi m. Okay, either you can use phi m is equal to tan inverse of this term, or else sine inverse of this term. All give the same answer. Okay, they are related by this triangle expression. Okay, from this, if I am taking this term to left side to the numerator and I am solving, I can get alpha also. Remember, if I have alpha, I can find out phi m. Similarly, if phi m is given, I can find out alpha. Okay. Next, if you want to find the magnitude at omega m, now we have find out the phase angle phi m. Okay, what is magnitude at omega m? Or this is the magnitude expression. This is the general form. So this is the magnitude at omega m means, at omega m, what is the frequency? 1 by tau square root of alpha. I put those things and solving, I get this expression, right? So I go to the next slide. Okay, so the maximum phase angle is, maximum magnitude at omega m, or the magnitude at omega m is 1 by square root of alpha. If I am going to express in dB scale, I will take 20 log 1 by square root of alpha. Square root becomes power 1 by 2. So 1 by alpha power 1 by 2. 1 by 2 comes before, so it becomes 10 log 1 by alpha. So I can make a mark in the slide here. Yes. So at omega m, the magnitude is 10 log 1 by alpha. We have, okay, so first what we did, we find out omega m, then we find out what is phi m. Now we find out the magnitude at omega m. Okay, the magnitude at omega m is 10 log 1 by alpha. Right? Okay. Now important point to remember, from the design point of view, suppose if the phase lead is given is more than 60 degree, we have to split it into two separate lead networks of equal angles. Suppose 66 degree is given, means what I have to do? One lead network for 33 degree, another lead network for another 33 degree. Okay, this is due to avoid the attenuation. Okay, right. Commonly, we will select the alpha value as 0.1. Okay, here I have written all the formulas consolidated. So this is the general form of the lead compensator. In a lead compensator, 0 comes very close to the origin, followed by the pole. Okay, so this is an pole 0 plot of a lead compensator. So this is the magnitude, this is the phase angle, what is omega m, what is phi m, and what is the magnitude at omega m, and what is the relation between phi m and alpha. Okay, and other things like alpha is equal to ZC by PC is less than, ZC by PC is less than 1 and tau is greater than 1. Okay, you can understand, quickly you can refresh these formulas. I have written in a single slide itself. Okay, next we move into lag compensator. In lag compensator, this is a standard form of a compensator. Here 1 by tau, here it is 1 by beta tau. In lead we used alpha. Okay, but here in beta it is also ZC by PC. Alpha is also ZC by PC, but alpha is less than 1, but beta is greater than 1. Okay, when beta is greater than, what is the meaning? ZC is greater than PC. So ZC will come here, PC is, that is ZC is greater than the PC. So PC is very close to the imaginary axis. Okay, so if the pole is very close to the imaginary axis, we say it is a lag compensator. Okay, now simple mathematical manipulations, right? So this is another form of writing, right? Okay, so here beta is greater than 1. Why it is called a lag compensator is the phase angle of the output will be lagging. Lead compensator means output will lead the input. In lag compensator, output will be lagging. Lagging means phase angle is negative. Okay, in lead compensator, phase angle is positive. In lag compensator, phase angle is negative. That is, for beta greater than 1, steady state output has a lagging phase angle with respect to sinusoidal input. Okay, now what about the corner frequency? If you look at the corner frequency, this is one corner frequency, another corner which is smaller, this is smaller. Pole is smaller, then followed by 0. So denominator will work first, then the numerator. Lowest corner frequency is this PC, then next corner frequency is ZC. So denominator will work first, followed by the numerator. Okay, when the denominator is working first, what happens? When the denominator is working first, it causes minus 20 dB. After the second corner frequency, plus 20 dB will become added. So minus 20 plus 20, it becomes 0. Okay, so this is the magnitude response. Then what about the phase angle? You know, phi is tan inverse of omega tau minus tan inverse of beta omega tau. Okay, and we know the range of this is 0 to 90. For this it is also 0 to 90. We are going to subtract these two. Among these two terms, which term is more powerful? Here omega tau, here it is beta omega tau. Since beta is greater than 1, this term will function much better than this term. So since we have a minus sign, initially the phase angle will be negative. Okay, this is more powerful because beta is greater than 1. Inside the bracket, we have a greater term than this term. So the phase angle will be negative. Then together what happens at high frequency? This is 90, this is 90. Together it goes towards 0. 90 minus 90 is 0. So low frequency both are 0, starts at 0. At omega high frequency both are 90, it becomes 0. In between it goes to the negative phase angle. Okay. It's very similar to what we have seen in the for a lead compensator, the same thing. So here omega C1 is 1 by beta, omega C is this term. So maximum frequency at maximum phase angle occurs at omega m, that is a square root of two corner frequencies. I get this value, and similar to that, there we got phi m is equal to sinus 1 minus alpha. In place of alpha I am putting beta here, right? Remember, alpha is less than 1, beta is greater than 1. Okay, and this circuit is a lag compensator circuit. I need this voltage. So the impedance is R2 by R2 plus 1 by SC divided by total resistance R1 plus R2 plus 1 by SC. Now properly you have to manipulate, right? Just taking things commonly outside, just solving. Okay, you can follow this derivation easily. Then we get this expression. Okay, so this circuit is a lag compensator because what is beta? Observe very closely. Beta is R1 plus R2 divided by R2. So beta is greater than 1 because numerator is greater than the denominator. Numerator is R1 plus R2, denominator is only R2. So it is definitely a lag compensator. Okay, right. Now other things, say I have just mentioned what is beta. Beta is greater than 1. What is ZC? What is PC? What is first corner frequency? Second, why this is first corner frequency? This term is smaller when compared with this term. So that is the lowest corner frequency and then second highest corner frequency. Okay, then how to find phi m? If beta is given, use this expression. If phi m is given, how to find beta? Okay, this will help you in the design part, right? Then we move on to the lag lead compensator. Lag lead compensator is a combination of both lag and lead compensator. So this is how the pole 0 plot looks like. Okay, we have a pole, then 0, another pole. So look at this expression. The 0 is at 1. So this is your I can say lag this is your lag part. This together you can mention as the lag. This is your lead. Lag, this is your lead. Okay, why I am saying this is lag? Lag means pole is coming close to the imaginary axis, then followed by the 0. Then we have 0, then pole. So this is the lead, this is the lag. Okay, so what is the 0 here? Minus Z1. What is the pole here? Minus P1. So minus P1 is the pole, then 0 is the minus Z1 is the 0. Then minus Z2 is the 0, then minus P2 is this pole. Okay, then this thing I can write in standard form, right? In a lag compensator I use beta, in lead compensator I use alpha. Alpha is less than 1, beta is greater than 1, some standard form. This is 1 by tau 1, here tau 2, right? So I have mentioned what is beta, what is alpha. Beta is Z1 by P1, alpha is Z2 by P2. Okay, now I can say an example, right? What about this? Okay, what is this? Whether it is lead or lag. Okay, which is having the lowest corner frequency? This is having the lowest corner frequency, right? So denominator will function first. So negative frequency will happen first, then followed by the numerator. So it is a lag. Okay, so this is lag part. Then what about this? Plus 3 divided by S plus 4. Okay, here which is functioning first? The numerator, because numerator is the lowest corner frequency is 3. So numerator will function first. Numerator is functioning first means positive phase angle. Then the denominator, the corner frequency is 4. So this will contribute to the positive. So negative, then positive. So it is a lag lead compensator. Okay, so if you're going for the pole 0 plot, it will look like at minus 1 I have a pole, then at 0, 0 at minus 2, then 0 at minus 3, then pole at minus 4. Okay, this is very similar to this, right? Pole 0 0 pole. So this is a lag lead compensator. This is lag, this is lead, together it is a lag lead compensator. This circuit is an example for lag lead compensator circuit. Okay, right? Hope you are getting some ideas, right? Always with respect to phase angle only we will say lag lead or lag lead, right? For a lag compensator phase angle is negative, for lead compensator phase angle is positive. For a lag lead initially negative, then it becomes positive, then it settles at 0. Let's look at that, right? So okay, we'll see that, right? So which is the first corner frequency? See, this is P1 is smaller, then Z1, then Z2, then P2. See, look at the order. P1 is smaller, then Z1, Z2, then P2. First the denominator will function, so it will cause us after omega P1 minus 20 dB. Then after Z1, this numerator will start functioning, so minus 20 plus 20, the net result is 0 dB. Then after Z2, this numerator will function, so it is numerator means plus 20 dB. After omega C4, this denominator will function, so the net result is 0 dB. So this is the magnitude response of a lag lead compensator. Then what about the phase? Initially it is lag coming in negative, then it for lead networks goes to positive, then settles at 0, but it never crosses 45 degree. Keep in mind, right? So this is the magnitude and phase response of a lag lead compensator. Okay, then other some interview questions like thing, right? If it's a lead compensator, I can say it is a high pass filter. High pass filter means at low frequency omega 0 it will not permit, at high frequency omega infinite it will permit. Lag compensator is a low pass filter. That means at low frequency omega 0 and very low frequency it will permit, at high frequency it will not permit, it will block. Then what about lag lead? lag lead is a band pass filter. Band pass filter means high frequency it will not permit, sorry, low frequency it will permit, as well as high frequency it will not permit, right? But between high and low it will permit, right? So between that band it is permitting, so it is called a band pass filter. Then lead lag compensator. Lead lag compensator, this you have to think about, right? I have explained about lag lead, no? Then how does a lead lag will be? Yes, lead lag will be like 0, pole, pole, 0. Okay, so this is, let me say this is -1, -2, -3, -4. How does the transfer function will look like? S plus 1 divided by S plus 2 into S plus 3 into S plus 4. So this is an example for lead lag compensator. Lead lag compensator is a, it will permit low frequency, permit high frequency, in between it will not permit. So it is a band stop filter, but this is very rarely used, right? That is why we study about lead lag and lag lead compensator. We are not worried about the lead lag. Okay, so lead lag compensator pole 0 plot will be looking like this, right? It is opposite to your lag lead. Simple. Okay, I hope you enjoyed the lecture. Keep watching the channel for more videos. We are happy to help you. Give your feedback in the comment section. More videos are coming in these topics. Keep watching. Thanks for listening. Happy learning.